Hi, my name is Gary Millett. I'm going to be your guide for this next topic. And our first presentation, topic number 1, is basic sensor theory. So, there's an introduction to sensors. And in this section, we'll start by giving a quick overview of legacy sensors. So, what is a sensor? Well, by definition, a sensor is a device that can take some physical parameter and convert it into a signal that can be measured. The devices that are used to inform the control system about what is actually physically happening in a process are known as sensors. They're also known as transducers sometimes. And that would be a device that converts or transduces a physical parameter. And again, typically to an electrical signal. The control system in this case is a closed loop control system, which needs a sensor or again a transducer to operate. So, if we take a look at standard physical parameters that sensors can detect, they are kind of delineated here. Say position, which is the location of something within the system, proximity, nearness in space, speed, that would be rate of motion, and that could either be linear or angular, revolutions per minute we'll say. Pressure, that could be atmospheric or fluid or gas, could be barometric pressure. Flow rate, again, fluid or gas, could be gallons per second or cubic feet per minute. Temperature could be ambient and or process temperature, and humidity, ambient and or process humidity. And again, these are very typical of what we use for systems. And that previous list is certainly not complete by any means, but represents the physical parameters typically sensed for devices or systems that are mechanical in nature and characteristically include some type of motion of the mechanical parts of the system. Also, there are a host of electrical parameters and quantities that can be sensed or measured, such as, I'll just go through the list here, voltage V, current I, resistance in ohms, conductance G, inductance L, capacitance C, frequency F, power W, etc. Scientists and researchers are working on new sensors continually and introducing them for new applications. We can also sense or measure field quantities or parameters such as electric and magnetic fields, electromagnetic energy, radiation, luminosity, and so forth. A little over a year ago, a new quantum sensor was introduced. I put a link in here to it, and it's a quantum sensor that can sense the entire radio spectrum. More recently, through the use of microelectrical mechanical systems, or MEMS, devices, and other sophisticated uses of technology, new sensor devices have been developed that can sense physical parameters other than those just from the mechanical world, including many that have defied detection by yesterday's technology. So we've extended and expanded what we can measure with sensors. Some of these new sensors have a basis in various familiar scientific disciplines. Excuse me. Physical, like optical, photonic, and so forth, chemical, biological, and so on. These new sensor technologies, combined with advances in embedded control and emerging wireless technologies, have given rise to the prediction of a vast array of new applications that will enhance the human condition in the near immediate future. So we will not spend much time with position, speed, and temperature sensors, since most of us are somewhat familiar with these devices through our life experiences. Instead, we will make some observations and generalizations about these devices and look at how they have become digital in nature. Most legacy sensors for position, speed, or temperature will use a source of electric power and a circuit along with a physical sensor to convert the sensor status, that is the position, speed, or temperature, into an electrical voltage or signal. Today, that electrical signal is digitized by an A to D converter to provide a digital or binary signal that can be interfaced to a microcontroller for processing. Remember our automobile sensor example? Here's again a picture of that. So recall our automotive fuel injection system from before. Note the signal labeled sensor power 5 volts coming from the ECM. That's more or less in the center of that diagram. This voltage supplies the power to the various sensors. The throttle position sensor, TPS, is the gas pedal. The output voltage of the TPS is proportional to its position. For example, not pushed might give you 1 volt, pushed halfway 2.5 volts, pushed to the floor 4 volts. You might question why it doesn't go from 0 to say 5 volts. Again, we want to tell the ECM that there's something there, that it's working. If we don't get something within a range of 1 to 4 volts, the ECM will take and cause an indicator to light up, or the check engine light, or what's called the MIL light to come on. That's the malfunction indicator lamp is what MIL stands for. So again, that's what we might use sensors for in the automotive system. We continue on with this example. The ECM program will check the output from each sensor to control the amount of gas that is injected into a cylinder and the exact timing of this fuel injection. Typically, there are several modes of operation that the ECM operates in. If one starts the automobile and the outside temperature is cold, the ECM will run a certain program to compensate for this condition. Once up to operating temperature, and that would be measured by the engine coolant temperature sensor in the top middle, what happens is another program will take over. When one is accelerating, another program; when idling, another, and so forth. So depending on what the conditions are, different programs might run to control the electronic fuel injection. A few more observations about our automotive EFI sensor example. One sees in our example that the various sensors are all connected to a sensor bus. The sensors all measure different physical parameters, and the sensor bus is interfaced to the ECM, which outputs control signals to the process that is being controlled. So one could consider the sensor bus to be the network that links the sensors, but as one can see, this network does not extend past the local ECM used to control the fuel injection system. There are interfaces to the outside world, OBD2, Onboard Diagnostic System 2, and MIL, again malfunction indicator lamp. However, it is necessary to be either connected to them or to be observed. The MIL light is a check engine light. So let's take a look at some legacy sensors like position. The fuel injection throttle position sensor, the TPS, just mentioned, is a good example how one typically measures position. A voltage is applied to a circuit that is linked mechanically to some physical system, and the circuit converts the position of some part of the physical system into a proportional fraction of the applied voltage. The position could be displacement, an amount of rotation, a position in 2D space or 3D space, etc. So continuing with this, depending upon the type of position being sensed, that is 1, 2, or 3D, this will determine the size of the data array, 1, 2, or 3 elements of sensor data, in the case of the 1, 2, or 3D. The use of different coordinate systems will require conversions between X, Y, and Z, and the new coordinates or vice versa. You might want to take a look at this link for Wikipedia's take on coordinate systems. It gives you relationships between different coordinate systems. Rotational displacement will bring in angular dimensions, and in each case there needs to be a starting reference point. For example, 0, 0, 0, or say 0 degrees. That brings us to the idea of how do we actually take our analog world. Temperature is continuously variable, speed can be continuously variable, humidity and so forth. How do we convert that to digital data that can be used in, say, a microcontroller? So let's stop for a moment to consider how the sense variable is presented to the control system. The analog sensor output will be converted to a binary or digital representation for input to the digital microcontroller. This process will be accomplished either externally by an A to D converter IC chip, or by the microcontroller itself via, say, an on-chip A to D converter. The precision of the conversion is dependent upon the number of bits of the ADC. So before we get into how this happens, we should know about the sampling theorem, the rules of conversion. A long time ago, several people came upon this conclusion that in order to retain all the information contained in the analog signal, one must periodically sample the signal at a rate of twice the highest frequency in the signal. This is known as the Nyquist, and I put in there et al. Criterion because there's about 3 other people that are not as well known. It would be a long list of names, so we'll just say Nyquist. If one does not follow this rule, an effect known as aliasing can occur. Now, what is aliasing? Well, this effect will cause information to be lost or masked by other spurious signals generated upon conversion back to the original waveform / signal by a digital to analog converter, or a DAC. What this all means is that one must sample the original signal at a rate that is 2 times the highest frequency component contained in the signal. An example of this is a voice signal with frequency components from, say, 0 to 2500 Hertz must be sampled at least 2 times 2500 or 5000 Hertz rate. And as an additional criteria, furthermore, the sampling must be periodic in nature, that is, spaced at precise regular time intervals. Most of the time this is achieved by using an electronic clock, that is, an oscillator that puts out periodic pulses with precision timing. So, how do analog to digital converters work? Well, how often the A to D conversion process needs to happen depends entirely upon the control system and what type of process is being controlled. There are different types of A to D converters, and which one you use depends upon how fast the thing has to do the conversions. A rapidly changing physical parameter will need speedy sampling conversion to keep up with changes, while a slowly changing physical parameter will not require as many samples or conversions per second. Furthermore, to prevent the control system from becoming unstable or oscillating, one might limit the presentation of new data to it. Control systems that try to overreact to inputs can become unstable. So, how about a home heating cooling system? This uses a process called hysteresis, readjusting the set point once it is reached to prevent rapid cycling of the system due to small changes in temperature. It's one thing we can do to prevent that oscillation. The rapid cycling of a system can cause premature failure of mechanical system components, which is not desirable by any means. If you have a heating system that's in the wintertime constantly calling for heat and then shutting down, calling for heat quite rapidly after that, you might want to check the hysteresis setting. So let's return to our automotive fuel injection system as another instructive example of how often sensor data is needed. And back in that diagram, back on slides number 8 or 9, the various sensors for our fuel injection system will need to be updated at different rates depending upon the parameter being measured. For example, the engine coolant temperature or ambient temperature, those are typically slowly changing physical parameters, may be sampled less often than the engine timing, that's the cam position sensor, the NOx sensor, and so forth. And you have to see those quite often. All the data from the various sensors is important to the vehicle's operation, but typically the data's rate of change varies for each sensor. Again, you start a car early in the morning, and it turns out the engine coolant will be low, and it'll slowly get up to its operating temperature. What about the detailed operations of an ADC? Well, the ADC subsystem takes in an analog signal and outputs a binary digital word that represents the value of the analog signal. At this point, the ADC output might be either stored, further manipulated, or both. Typically, an ADC will have a range of operation, that is, an input voltage range that goes from, say, 0 to a full-scale reference value. The ADC input voltage range might be bipolar. For example, it could go from 2.56 volts, minus 2.56 volts to plus 2.56 volts, or it could be unipolar, going from, say, 0 to 2.56 volts. So here's a block diagram of an ADC, and on the right hand side you can see the various inputs to the chip. There's voltage, power, and ground down the bottom. Up top is the reference voltage, which is critically important to this. There's a starter conversion input, a clock input, the input itself, the VIN, an analog input signal. On the right hand side there's an output data word, N bits. In this case it looks like there's 8 lines that come out, so it would be an 8-bit A to D converter as an end of conversion signal. So let's take a closer look. An analog input voltage less than or equal to V reference is applied to VIN. V reference determines the full-scale range of the ADC. A clock pulse signal is necessary to facilitate the operation of the IC's internal conversion electronics. And we mentioned before there's many different types, well not many, but a few different types of ADCs. The startup conversion signal initiates the conversion process, and the end of conversion signal indicates the completion of the process. Typically these signals are connected to a microcontroller. An output data word is presented on the output lines for the duration of a sample time. So when the end of conversion pulse comes, the data is now on the output data word lines. A little more detail here. The output binary digital word is given by the following equation, where the right side is in decimal, that is base 10, normal decimal notation, and rounded off to a whole number, but the output word is in binary, that's the left-hand side. So notice the output word is VN times 2 raised to the n power minus 1, where n is the number of data lines coming out, number of bits, divided by V reference. So the next slide should show us an example. So here's an example. Notice that in this one, in the diagram, V reference is 2.56 volts and VN is 2 volts. So we're okay with that. We've also labeled the data output lines from most significant bit, the top one, to least significant bit, the bottom one. So for this example, n equals 8, V reference is 2.56, analog input signal VN is 2 volts. So doing the math there, the output word is VN, which is 2 times 255 divided by 2.56, which gives us roughly a 199. We rounded it off. Therefore, the output word should be 110001111. And if you do the math for this, you'd see the most significant bit was worth 128. The one below it is worth 64. So 64 and 128 is 192. The last 3 bits of 111 are equal to 7. So 192 plus 7 is 199. If the input signal level is such that the decimal value on the right-hand side of the equation is in the middle of 2 whole numbers, for instance, it might be 58.5, the binary output will be either 58 or 59, with a high probability that the least significant bit, the LSB that is, will be flickering on or off. That is either a 1 or a 0. So the rest of the bits would be stable, but that last bit would be flashing back and forth between 1 and 0. And this gets us to the idea of ADC resolution. So the resolution of an analog to digital converter depends upon the number of binary output bits. The more output bits, the better the resolution of the finer the detail that can be captured. An 8-bit ADC can produce 256 different output levels, all zeros to all ones. If a reference voltage of 2.56 volts is used, then the resolution will be that voltage divided by the number of levels, 256, or 10 millivolts. So that is, it will take a change in the amplitude of the input voltage of at least 10 millivolts to change the state of the least significant bit, the LSB. This also means that all inputs in a 10 millivolt range will be encoded identically. Again, the problem with what we call quantization of an A to D converter. If, for instance, we had a 12-bit ADC, that can produce 4,096 different outputs. With the same reference voltage as the last example, the resolution would be 2.56 volts divided by 4,096, or 625 microvolts. 16 times the resolution of the 8 bits. Of course, 12 bits is 4 bits more. 2 to the 4th is 16. Today, it's quite common to have A to D converters with 10, 12, 14, 16, and even 20 binary bits of resolution. A 16-bit A to D converter has a resolution of approximately 39 microvolts with a V reference of 2.56 volts. Now you start to get down into the noise. The Microchip PIC24 family of 16-bit microcontrollers has on-chip a choice of high-performance 10, 12, or 16-bit A to D converters for interfacing with the analog world. Now, this is a typical A to D converter setup. We haven't talked about all the details what we need. Notice in this block diagram we have an input analog signal, goes through a low-pass filter. There'll be a signal conditioner, which is either an amplifier or an attenuator. Then you have the A to D converter, the clock that drives it, and the data output word. So an analog signal to be digitized is low-pass filtered to restrict its frequency range, conditioned to be in a certain voltage range, and digitized by an A to D converter that is clocked to operate in a certain sampling, at a certain sampling rate or frequency. The output's a new data word. Multiple bits is indicated by the bold line every time a conversion is initiated. Now this slide here shows the PIC24 family of 16-bit microcontrollers in block diagram form. And we're not really worried about the stuff on the left-hand side of the diagram. That relates to the CPU and so forth. What we'd like to do is take this look at the stuff on the right-hand side. So on the right, one sees a red peripheral pin select block, which indicates that the various peripheral pins can be configured to be connected to any one of the 16 blue blocks or functions to the left of that red block. One of these blocks is labeled ADC 10-bit 16 channel, which means there are 16 A to D converters that convert data into 10-bit words. And right next to that one, another block to its right is labeled ADC2. That's a 10/12-bit 32 channel, another A to D converter. So what about digital to analog conversion details? Well, a DAC IC takes in a binary digital word and outputs an analog signal level proportional to the magnitude of the binary digital input word and the value of V reference. So like the ADC, the resolution of the DAC is also proportional to n, the number of input lines, or bits. The output signal level of the DAC can change every time a new binary word is applied to it. So for instance, if input words are applied at a rate of 20,000 per second, this frequency will also be present in the DAC's output signal. Now this added signal is undesirable since it was not originally there and should be suppressed as much as possible unless it doesn't affect system operation. More details. Furthermore, the output of the DAC can change abruptly if the magnitude of the input word changes greatly. This effect can cause spikes in the analog output signal. So, to remove any extraneous signals, that would be the data input rate, harmonics of the data input rate, and spurious frequencies due to spikes, what we do is for the analog output signal of the DAC, we take and place a low-pass filter after the DAC to smooth out the analog output signal, which is typically slowly varying compared to the spurious signals. Well, I don't have a diagram of that yet, but we will. So here's a typical DAC IC chip. And notice this one, the multiple lines are on the left-hand side, the input binary data word. Again, the V reference, V power and ground, and then an analog output voltage, V out. So the binary input word is applied to the N input lines. The DAC IC chip outputs a voltage from 0 volts to just a little bit less than V reference, depending upon the binary input word. An input of all zeros yields an output of 0 volts, while the input of all ones yields a voltage of just under V reference. The output voltage from the DAC is given by the following equation. V out equals input times V reference divided by 2 to the n, where n is the number of input lines and inputs is the decimal equivalent of the binary input word. So we'll probably have an example coming up, and sure enough, so now we have V reference of 2.56 volts. Our input binary data word here is 10101100, which I believe is 172 in binary. So over on the right-hand side for an 8-bit DAC, n equals 8, and if we stick that into the equation here. Reference is 2.56 volts. Input word is, again, 172 decimal. Then the analog output voltage Vout is 1.72 volts. So this one takes the binary input and directly converts it to a voltage. For a binary input of 10101101 or 173 decimal, the output would be 1.73 volts. Note that this is a difference of 0.01 volts or 10 millivolts, which is, you might recall, the 8-bit DAC's resolution. So again, practical matters for DACs. Today it's possible the actuator of the control system can handle a digital input signal directly from the digital control system, and therefore a DAC is not needed. Furthermore, today's microcontrollers typically do not come with on-chip DACs. After I've told you all this, it turns out that, lo and behold, instead on-chip pulse width modulators, or PWMs, are more common, and they can perform the same function as a DAC. That is, they can provide an analog output signal under program control. Albeit they are not high-speed devices, usually not a problem, however. So depending upon the microcontroller chosen to implement the digital control function of the overall process control system, a DAC IC may or may not be required to implement a system. As mentioned already, the resolution of a DAC depends upon the number of input lines or word size n. For a DAC with V reference of 2.56 volts and n equals 8, the smallest change in the output signal is 10 millivolts, whereas a 12-bit DAC could provide an output difference of 625 microvolts per decoded level. So, as I mentioned earlier, here's a typical DAC setup with a low-pass filter in the output. So you see the input data word bold because it's many bits coming into the DAC. Then there's the low-pass filter, the LPF, and the analog output signal. So the digitized value, the data word, is applied to the DAC. The DAC produces an output voltage proportional to the digital word it sees and the DAC's input reference voltage. The DAC's output signal is basically a pulse amplitude modulated or PAM signal that contains a low frequency signal, the original digitized signal, a strong frequency component at the sample frequency, and harmonics of the sample frequency. So that's the reason for the low-pass filter. The low-pass filter passes the original signal, removes the superfluous high-frequency components. Most people don't see this with DACs. If you're just told that it's going to put out a DC voltage, that's given by whatever the input data word is, that's where people usually leave it. But the truth of the matter is, in practice, if the input data word is changing because there's, say, 100,000 samples per second, you're going to see that 100,000 kilohertz signal on the output of that DAC, and it wasn't there when you actually did the the A to D conversion. So it turns out that we need a low-pass filter to get rid of that sampling frequency. Now here's a same figure we had before, the PIC24 microcontroller. We already talked about what that red block does. It picks out which one of those 16 blocks in blue operates, and you might notice that there is no D to A converter there, no DAC. However, there is, if you look in the left-hand column, about 3 from the bottom, an out comparator / PWM. So this output comparator, PWM, as I alluded earlier, there's not a DAC block for this, but the PWM can be programmed to output a desired voltage and thus serves the function of a DAC. Excuse me. So there are resources out there. If you go to YouTube and do a search for ADC or DAC, you will find some good video resources that will help you understand how these devices work. I've got a link here for a video about ADCs that highlights the Arduino microcontroller. So a summary of all this, sensors for basic physical phenomena have been in existence a long time. We have deployed sensor-based control systems into many modern innovations. The electronic fuel injection system of modern automobiles is a good example, as well as various kitchen appliances and home/building HVAC systems. Today we have evolved these control systems to be digital in nature, and have likewise added electronic ADCs and DACs to interface our analog sensor and actuator inputs and outputs to our digital control systems. That's it for this presentation. There are several more about this topic.